All right, so first up, we're going to have hydrostatic pressure, which there are going to be two kinds. One is going to be in liquids and the other in gases. So when fluids are in static equilibrium, there's only pressure, force, and gravity acting, which is going to result in the given equations that we have, which is P2 minus P1 is equal to negative gamma multiplied by Z2 minus Z1, which is basically Z2 and Z1 are just basically going to be our heights. And in terms for the mercury barometer, it's just going to be PA is equal to gamma of mercury times H, which is obviously equal to Z as well. And it's using the upper equation, but P1 is basically zero since mercury has a low vapor pressure. And the main takeaway from that, from the equations, is that pressure only changes with vertical height change, no horizontal change. And then for gases, we're going to have this given equation with all the constants labeled below it. And this results from the ideal gas law. Okay, and next up, we're going to have the manometer, which is used to measure pressure differences between 2 points with the given equation. Obviously, this equation is not going to apply to all circumstances since every scenario is going to be different. But the main takeaway is you're going to have your starting pressure, which we have right here at A, and then our ending pressure over at here at the open end where PA is, which you can see. So we have the beginning and the ending right here. And then we have multiple fluids to be dealing with, which is why we have multiple gammas here. But the main takeaway from this is that you're going to have your gamma multiplied by the height change. So for right here, we're going to be dropping to here, which pressure increases when the depth increases as well. And so when we move over here and go up, it's going to be a negative change since the pressure will be decreasing since we are increasing in height. And then the units are going to be resulting in newtons over meter squared or pound force divided by foot squared. Next up is Archimedes' law, which basically says vertical buoyancy force is equal to the weight of the fluid displaced, which is going to result in this equation right here, which is buoyancy force is equal to gamma of the fluid that the body is in, multiplied by the volume displaced by the body. And obviously, since it's a force, we're going to have units of newtons or pound force. After that, we have stability, which essentially the main takeaway from this is the restoring moment. If a body is stable at any point and it's disturbed, it will create a restoring moment to return to its original position. As you can see right here, this one is stable, so there's no restoring moment occurring. Over here, we have a small disturbance angle. And as you can see, the metacenter and the center of gravity run through the line of symmetry as it does in this one. But instead of the center of buoyancy being directly in line with everything else, since it's no longer stable, it's going to be shifted over, but the line of action for buoyancy force is going to run through the metacenter as well. And a metacenter above the center of gravity is going to have a restoring moment, while if it's below, it's going to have a overturning moment.
So here we have a hydrometer. It's used to measure specific gravity. And in water, it's the mass of the device times gravity, which equals the buoyant force of water, which equals the specific weight of water times volume when it's submerged. And in a different fluid that's not water, it would be the mass times gravity of the device, which equals the buoyant force of the liquid, which equals the specific weight of the liquid times volume minus the area times height. And for specific gravity, it's just a ratio of the specific weight of that fluid over the specific weight of water, which equals the volume divided by volume minus area times height. For containers in motion, there's two types. There's linearly accelerating containers and rotating containers. For the change in pressure in linearly accelerating containers, it's the density times gravity minus acceleration. For the downward angle tilt, you would use tangent theta equals the acceleration in the x direction over the acceleration z direction plus gravity. And a different way to find change in pressure would be to use density times universal gravity, which is density times the square root of the acceleration in the x direction squared plus gravity plus the acceleration in the z direction, and all of that would be squared. For rotating containers, the change in pressure equation is negative density times the radius times omega squared in the I direction minus gravity in the K direction. And to find the distance from a free surface, it would be Z. And so that would be the initial pressure minus the final pressure over the specific weight plus the radius squared times omega squared all over 2G. And to find the highest point from a free surface would be Z max, and typically Z naught is negligible. And so that would equal radius squared times omega squared all over 2G. And there at the bottom, we have the units for those. And here we have two images to represent the linearly accelerating and container in motion, and then the rotating container in motion. So on the left, we have the linearly accelerating one, and on the right, we have the angular acceleration or the rotating container in motion.
For the pressures of the forces on inclined planes, a lengthy proof yields that the specific weight, height from the centroid of the plane to the free surface, and the plane area have bearing on this force produced. The formulas on the left show a gauge pressure and a non-gauge pressure version, and in our case, we're working with the gauge pressure version most of the time. This is because the ambient pressure parameter, PA, is ignored because it's usually acting on both sides of the plate. The center of pressure denotes the location of where the resultant force from the previous slide can be placed along the body. The formulas on this slide calculate the value relative to the center of gravity of the object of interest, and the center of pressure is almost always further down than the center of gravity. This location is calculated with the specific weight, the centroidal moments of inertia, the angle of inclination of the plane, and the resultant force. For symmetrical cross-sections, the XCP is 0. For forces on curved surfaces, the resultant force is computed by separating into horizontal and vertical components. For the horizontal component of force, we project this curved surface onto a vertical plane normal to the component and use the standard FR formula we saw in previous slides, but with the projected plane as the area. For vertical components of the pressure force, we look at the weight of the entire column of liquid and atmosphere above this curved surface of interest, and we do this by multiplying the specific gravity by the volume of the section we are interested in. The last topic we'll go over before jumping into the problem is layered fluids. We can't just use one formula from the previous slides for these scenarios, as the slope of the linear pressure distribution changes from fluid to fluid. However, we can separate these layers and sum the forces and moments created by the system as shown by the formulas in the previous slides, and summing these forces and moments helps us find different characteristics of the system, like the center of pressure or the total force exerted on the bottom surface. Each layer of fluid's hydrostatic pressure is impacted by the one above it, as seen in the calculations on the right.
Hello, my name is Vince, and we will now be taking a look at problem number 1 for the presentation problems. First, let's just take a moment to read through the question and see what's being asked of us. Feel free to pause the video at this point and read through the question for yourself. After reading through the question, we can highlight what pieces of information are important to us. The first bit of information that is important to us is that the quarter circle gate is 7 feet wide into the paper. So this is going to be going into the X direction. Now, the second bit of information that is important to us is that the gate rests against a smooth wall at A, right here. This lets us know that there is no friction that comes into play at this contact point. A useful hint that we are given is that the maximum force that the wall can withstand is 9,200 pound force. We are told that the gate is hinged at B, and also that the gamma of water is 62.4 pounds per cubic foot. Through the diagram, we can also get the dimensions of the gate, which we can see here, 4x4 quarter circle. Now we must clearly define our objective, which is to determine the maximum height that the water can be at without the wall breaking. Water level right here. So just went ahead and wrote down the objective and as well as any helpful hints. Now moving on. Now let's just take a brief moment to note what bits of information that we do have. We were given that the gamma of water is 62.4 pounds per cubic foot, and that the maximum force the wall can withstand is 9,200 pound force. Since the gate is only touching the wall at point A, it is viable to deduce that the wall will have a reaction force onto the gate, which is 9,200 pound force. And below these bits of information is a diagram that shows the projection of the quarter circle gate onto a vertical surface, which will be useful in determining the horizontal force of water, as well as the coordinate system that I will be using to solve this problem. Here are the coordinate systems, and here's the projection of this quarter circle gate onto a vertical plane. All right. Right here, we're going to be solving for the horizontal force that the gate is experiencing. The equation for the horizontal force is given by gamma times hc times A. We are already given the value of gamma, but how do we determine hc and A? Well, hc is determined by finding the vertical distance from the free surface to the centroid of the projected vertical planar surface, which was sketched earlier. So if you direct your attention to the diagram below, we can see that the height of the free surface is h max, and the centroid of the quarter circle gate's projected surface is at 2 feet, which right here, 2 feet. From this, we can determine that hc is equal to h max minus 2 feet. A is then given by taking the area of the projected surface, which we know is 4 feet, multiplied by 7 feet, which will give us an area of 28 square feet. If you're unsure, you can go back to the previous slide or rewind a couple seconds to just make sure that these dimensions are correct. By fully multiplying out, we get a horizontal force in terms of H max, which is right here. Now that we have determined the horizontal force, we need to find out where the horizontal force will act. If you refer to the diagram to the right, to the left, you will be able to see how the different vertical distances are denoted, which will help you follow with how YH is determined. First, we will start with YR, which represents the distance from the free surface to the point where the force acts. As you can see, this is YR. YR is calculated by the equation shown. It's given by YC plus IXX comma C over HC times A. Now, we've already determined what HC is, which is given right here, and what A is, but we need to figure out what IXXC is. Well, IXX, or the second moment of the area about the centroid of the vertical projected surface, this is going to be calculated by the equation 1/12 times BH cubed. According to the coordinate axes that I displayed earlier, our base will be 7 feet and our height will be 4 feet. And we can now solve for IXXC, which will give us a value of 37.333 feet to the 4th power, right here. Now we can solve, plugging back what we just solved for right here back into our YR equation. We can get YC plus 37.333 feet over H minus 2 times 28 feet squared. Now I just went ahead and simplified this right here down below. Alright, so now that we've done that, we're going to obtain the value of YC, which is the distance from the free surface to the centroid of the vertical plane surface. We take the maximum height and subtract 2 feet, which will yield H max minus 2 feet. H max minus 2 feet. Alright, which we can now plug this into our final YR equation, which will give us this equation right over here. As you can see, the two H maxes will cancel out, leaving us with 2 feet minus 1.33 over H minus 2 feet. Finally, we are able to start solving for H. I would like to preface this by saying that from this point forward, the H max variable will be changed to just H in the interest of saving space. To start solving the process, we will utilize a free body diagram to help visualize the forces on the quarter circle gate, which will be up here to the left. Starting from the top, we have the reaction force of the wall on gate at point A. We already know that the wall can withstand a maximum force of 9,200 pound force, and therefore the maximum reaction force at A is 9,200 pound force. Now we will work our way down to the horizontal force, which will be denoted as FH. And finally, we have our pin connection at point B. From statics, we know that the pin connection at point B has both vertical and horizontal reactionary components. Now we will set up a moment equation which will allow us to ultimately determine H. We have chosen to take the moment about point B since it's the point with the most unknowns. By doing so, we see that we get the following equation off to the right of the diagram, which is displayed right over here. Alright, the reaction at point A, which we know to be 9,200 pound force, is multiplied by a distance of 4 feet, which is given in the diagram. And since it's going to be in the counterclockwise direction, we'll interpret it as a positive moment. Then we will take into account the horizontal force FH and multiply it by our distance YH. Now since it's going in the clockwise direction, we will interpret it as a negative moment. Now setting the two moments equal to each other, we can finally solve for a maximum height. In the interest of saving time, I will forego explaining the algebra that went into solving H. However, as you can see, we subbed in f of h for what we solved for earlier into these equations, as you can see from up here. And going through all this algebra, we end at h is equal to 13.31 feet.